Hello, my name is Nino, and this is my test one. So I chose problem 16, which is to use the repertoire method to solve the general four-parameter recurrence. We have g of 1 equals alpha, and g of 2n plus j equals 3g of n plus gamma n plus beta j for j equals 0 and 1, and n is greater than 1. So the first thing I'd like to discuss with this problem is the goal. So this is a repertoire method problem, which typically involves turning a recursive function into a closed form function. Now, this problem's a bit strange, but the goal remains the same in that we want to turn this strange four-parameter recursive function into a function like g of n equals a of n alpha plus b of n beta 0 plus c of n beta 1 plus d of n gamma. The next goal would to be find a of n, b of n, c of n, and d of n, plug those into our g of n, and then all we have to do is plug in our value in to find g of n. In this case, it's going to be a bit strange. Alpha, beta 0, beta 1, and gamma are going to be undefined until we find values to fit it, or your given values. But anyway, the first thing to do with this problem is to form a function table using the four-parameter recurrent function and come up with a table of g of n values for each n. Now, what's important with this function table is that the coefficients for alpha, beta 0, beta 1, and gamma are the sequence for your function of a of n, b of n, c of n, and d of n. So we have to use those to come up with a function that describes that sequence. So the first thing to do is to find the function a of n, which gives us the values for the coefficients of alpha. So the first thing you want to do is to make a table of a of n values. The first thing you'll notice is we have powers of 3. So we have 1, 3, 9, 27, 81. And the second thing to notice is that a of n repeats itself, and the number of times it repeats itself are in values of powers of 2. So we have 1, 1, 2 3s, 4 9s, 8 27s, and so on. So we know a of n has something to do with 3 to the power of something and 2 to the power of something. So if you're going about this based off the textbook, you might set n equal to 2 to the power of m plus l, make a chart of m values, and we could describe a of n as 3 to the power of m, where you get m from n equals 2 to the m plus l. Now, the way we're going to do it is if you turn n into binary, and then you turn a of n into ternary values, you'll actually notice that we're taking the binary number n and we're just keeping the lead bit and wiping the rest into zeros and then converting it into base 3. And this will give you the sequence a of n. So this is what we are going to use. So now we want to find the function b of n. So once again, we make a chart of b of n values. So the first thing you might notice is that we have powers of 3. Once again, we have 3, 1, 9, so on. But now we have 13, 12, 10. These aren't powers of 3, but you might notice that these are powers of 3 added together. So 13 is 3 squared plus 3 to the power of 1 plus 3 to the power of 0. So once again, if we turn n into binary and then we make a chart of b of n values in ternary or base 3, you'll notice that b of n is the inverse of n. So if we have 13, we turn it into binary, which is 1101, you'll notice that for b of 13, we have 3, which is in ternary it's 0010. And you'll notice that we go from 1101 to 0010. So in this case, we're going to take our number n in binary, we're going to invert the ones and zeros, and then we're going to convert it to base 3, and that gives us our b of n values. So now we want to find c of n. So once again, we make a chart of c of n values. And you might notice that c of n is almost exactly the same as b of n, but the order of the groups are reversed. So instead of 0, 1, 0, 4, 3, 1, 0, we have 0, 0, 1, 0, 1, 3, 4, and so on. So we could assume from the start that we're taking a number n in binary, manipulating it, and then converting it into base 3. So if you make a chart of n values in binary and then a chart of c of n values in ternary, let's say we go for n equals 13, which is in binary, it's 1, 1, 0, 2. And then C of 13 is 10. And so 10 in ternary is 0, 1, 0, 1. And you'll notice that for every value of n and C of n, you're taking the binary number and you're removing the lead bit and then converting it into base 3. And so our C of n function can be described as this here below. So now to find D of n, based on A, B, and C, you might take a chart of D of n values. You might turn n into binary, D of n into ternary, and try to find some connection in between. In this case, I don't believe there is one. So instead, we're going to find D of n in a different way. And if you go back to problem 16 in the textbook, you'll see hint, try G of n equals n. So we're going to do that. Okay, so we're going to express G of n as A of n alpha plus B of n beta 0 plus C of n beta 1 plus D of n gamma, and we're going to set that equal to n. So the next thing to do is define alpha, beta 0, beta 1, and gamma for G of n equals n, which you could do by going back to our function table and setting those values equal to n. And from G of 1 through G of 4, you'll be able to solve that alpha equals 1, beta 0 equals 0, beta 1 equals 1, and gamma equals negative 1. So if we plug these into G of n equals n, it simplifies down to A of n plus C of n minus D of n equals n. So we want to find D of n, so we're going to rearrange this to get D of n equals A of n plus C of n minus n. And that's our D of n. Right, so now we have A of n, B of n, C of n, and D of n. But our D of n is expressed as A of n, C of n, and n. So we're going to plug what D of n equals into our G of n. And it now simplifies down to G of n equals A of n, parentheses, alpha plus gamma, plus B of n beta 0, plus C of n, parentheses, beta 1 plus gamma, minus n gamma. And this is now our final closed form equation for G of n, where A of n, B of n, C of n all equal these binary expressions. So now we're just going to verify real quick that our G of n works. So to find alpha, beta 0, beta 1, and gamma values, we're just going to set G of n equals 1 as a test, which will give us alpha equals 1, beta 0, and beta 1 equal negative 2, and gamma equals 0. If we plug those into our closed form G of n, it simplifies down to G of n equals A of n minus 2B of n minus 2C of n. So if we want to find G of 500, we first turn 500 into binary. We then use the conversions for A of 500, B of 500, and C of 500. And A of 500 equals 6,561, B of 500 equals 31, and C of 500 equals 3,249. If you plug these into G of n, we get G of 500 equals 1, and that proves that our G of n works. Here's a quick summary of our closed form G of n, and that's about it. Thanks for watching. Bye.